This is a test preview or test review material day, and you set the agenda. There's certain limitations. You can't just ask me to review everything. We don't have time for that. But you are telling me what you want to go over. And if you don't have anything to go over, then I'll go over Unit 4. We'll start the next unit. Well, I'm just saying, okay, you need to come prepared. I've given you lots of tools to be prepared. You can go over all the notes and the homework. You can go over the text. You can go over the practice test. Lots of ways you can figure out what you need to know to be prepared for the test. That's your job. The one thing you can't do is sit there on your phone. Joshua. Okay? You have to focus on what we're doing here today. Okay? Yes, sir.
What is the total overview of the test? Like what material will be tested on?
This unit is primarily about bonding, both covalent and ionic bonding. Okay? Now that includes, molecular shapes, but you figure out that from the bonding part of things. So, what? The shapes?
No, the bonding. Like what we did like Wednesday with water.
Oh, that would be molecular shapes.
Okay.
All right. Well, get out paper and pencil and your periodic table, guys. So Matthew, how many valence electrons does phosphorus have? I'm going to give him a second. He's looking up on 5 valence electrons. All right, very good. So you get 5 because if we're doing orbital notation, in fact, I think I've got the orbital notation written out for phosphorus here somewhere. With the orbital notation for phosphorus, we see that there are, in the highest level, the highest primary energy level of the atom phosphorus, that's the 3rd primary level, 3s electrons, there's 2 of those, and in 3s there's 2 of those, and in 3p there's 3 of those, and together all the 3 level orbitals make up the valence level for phosphorus anyway. So it's the highest energy level regardless of whether it's phosphorus or something else. So that's 5 valence electrons. The electrons in the highest primary level, those are the valence electrons. That's the valence level. You can look at the periodic table and kind of figure it out quickly, because in this row where phosphorus is, these electrons are corresponding to where we have sodium and magnesium here. That's the 2s electrons we talked about. And you got 1, 2, 3p electrons. Okay, so that tells you how many valence electrons. You have 5 valence electrons. So if we have 5 valence electrons, how many electron dots are we going to put around a phosphorus symbol for an electron dot formula, Jody? How many electron dots do we put around phosphorus? Yeah. Oh, that's what you meant by that. Okay, I got you. All right. I was a little confused by what she was giving me hand signals there. 1, 2, 3. 1 on each of the 4 sides and pair up somewhere. Okay. Let's put that together with chlorine. What do you say? Okay, here's chlorine. So, Joanna, how many electron dots do I put around chlorine? 7. 1, 2, 3, 4, and then pair up. 1, 2, 3, 4. Okay. And Amaria, how many electron dots or how many valence electrons does chlorine want to have?
8.
It's always 8. Only the small atoms like hydrogen don't want to have 8. Okay? And we say, again, want to because that's an easy way to understand it, but it doesn't really want anything because it's not alive. Well, we can do that through sharing. Okay, and so we do this sharing arrangement. So I had electron dot formulas. That's what the black part here, the black letters and the symbols are all about. But now I am sharing electrons. So phosphorus had 5. It shares 1 with chlorine. That gives it 6. Chlorine had 7. It's sharing 1. It's got 8. So chlorine's done, but phosphorus ain't there yet. Okay, so phosphorus has got 6 electrons right now. How about Shannon? How do I get more electrons for phosphorus? Yeah, another chlorine, sure. 1, 2, 3, 4, 5, 6, 7, and we can share those 2. Well, that gives this chlorine 8 electrons, but phosphorus is only at 7, so we still need another chlorine.
Wait, why'd you draw another chlorine?
We're trying to give phosphorus all the electrons it needs to have an octet for that valence level.
So you couldn't just take one that was paired with another one?
No, later in other classes in college and such, there are times when you can split up pairs of electrons. But for the simple stuff we do, we never break up these pairs of electrons. Okay? So where we're starting from is we don't break up the pairs. Got it? Got that?
Yeah.
Okay. So if somebody's dating, you don't break them up.
Yes,
No, you don't. You shouldn't. That's just mean.
unless they're unhappy.
All right. And so if I share these 2, now the phosphorus has the 8 electrons it wants, and the chlorines all have 8 electrons, and everybody's where they need to be more stable. Okay? But that's the sharing arrangement. So we started with the electron dot formula. Or you could call it electron dot notation. And now that we've done the circling of electrons, we have the sharing arrangement. So after we get the sharing arrangement, Mackenzie, what's the next step in this process trying to get to a molecular shape? It's a step-by-step process. These are the first 2 steps. What's the next step? The what? No, it's called a Lewis dot formula. It's kind of like an electron dot formula. We call it a Lewis dot formula. So with the Lewis dot formula, what we do is we squeeze shared pairs between the atom symbols. So between this phosphorus and this chlorine, we're going to squeeze them together. Okay? I squeeze them in between. And then between this phosphorus and this chlorine, we're going to squeeze them together. Or squeeze them in between. And between the phosphorus here and this chlorine, we're going to squeeze them together over here. We have to keep those lone pairs. They're still part of this Lewis dot formula. Now we could do a Lewis formula where we replace shared pairs with lines, but for the molecular shapes we don't really need to go there. We can stop with the Lewis stuff right here and go straight to the electron dot formula then. Okay, the electron dot formula, Mackenzie, is a 3-dimensional shape. Okay, so Joshua, how many sets of electrons do I have around that phosphorus?
4.
Yep. So if I have sets, to remind you, to reiterate, can be lone pairs, so there's a lone pair right there. Sets can also be the total group of electrons between any two atoms. And so in this case, I have 3 sets of 2 that are shared electrons, okay? For a total of 4 shared sets, okay? 4 sets to figure out what molecular shape we need, okay? So, what do you say? Tetrahedral, okay? There is a difference, let me just finish this first, between a tetrahedron and a tetrahedral. I'll show you both in a second, okay? For a tetrahedral, we're going to have the phosphorus in the middle. The atom to which everything else is bonded goes in the middle. And each of these sets of electrons get on the end of an arm. And they need to be equally spaced in space around that. And that's a tetrahedral shape like this. And I'll put those, there's a set of 2 on each of these arms because I got a set of 2 on all 4 sides of this phosphorus. So this is a tetrahedral. And we call this an electron pair shape. So I promised Matthew that I showed you a tetrahedron. Okay? So it's like the same as this, only on the end it's ON instead of AL. So a tetrahedron has 4 sides and 4 corners, and all the sides are triangles. Okay? Let me see if I can draw that in a way that makes some sense to you guys.
It's not just a square?
It's not a square. No, it's all squares have not a square. What is a box shape called? It's not a square. Cube. Okay, it's not a cube has squares on all the sides. A tetrahedron has triangles on all the sides. Okay. So if I have this, and I have a triangle over on this side, and I have this and a triangle over on this side, that puts a triangle on the bottom and the back. That's a tetrahedron.
Are we not ever have to do that?
No.
Okay.
In college, you may have to know that because there are structures that are actually tetrahedrons that you might need to know. There's a structure for sulfur that includes linked and separate tetrahedrons. So different types of sulfur might include this. All right, so the next step, what's the next step we're going to follow here? Let's see. How about we go to Aiden? What's the next? Yes. I was trying to move it all around, give it a shot, okay? What's the next thing I need to do, Aiden? I've got the tetrahedral electron pair shape. What's the next thing I need to do? Well, now y'all stop chuckling. He's trying. Okay, what?
Ain't that thing where you gotta put the symbols on?
You gotta do what?
The symbols on? Like how you got the P and then the Y and you go see it? Or that's all that?
You put the shared sets as
He's saying it
the
right.
element.
He is saying it right?
Yeah.
Okay, I'm not connecting here with what you're saying, okay? So what we're going to do here, Aiden, is the way I describe it is to redraw this same thing
All right,
first, okay? So we'll put a phosphorus in the middle, and we have an arm going up with a pair of electrons on there, and an arm going over here with a pair of electrons, and an arm coming out toward you. That's what this triangle is supposed to be illustrating. And an arm going back behind the paper. That's what the dotted line is supposed to illustrate. Okay, but then what we're going to do is replace shared sets of electrons with the atoms with which they are shared. Okay, so we have 3 chlorines shared with 3 of these sets of electrons. They're all the same. They're all two electrons. And it doesn't really matter where we put those 3 chlorines. Okay? It doesn't matter. With the shapes that we're dealing with, it won't matter where you put them. In college, yeah, there's some you get to that it matters where you put them. But for the ones we do, it doesn't really matter where you put them, okay? So I'm going to choose to put a chlorine over on this corner right here, and one that on the corner that comes out toward you, and one on the corner that goes back behind the paper here, okay? So I'm going to have a chlorine here, and we're going to have a chlorine out here on the front of this, and on this part that's going back behind, we're going to have a chlorine back here.
Teachers, pardon the interruption. Any student who should have gotten their lunch during first lunch who has not received a lunch, please allow them to go to the cafeteria at this time.
And then we got this lone pair of electrons up here that isn't bonded with anything, so they're going to stay there.
Can you zoom in?
That's a tetrahedral modified pair, electron pair shape?
You got it.
Thank you.
So it's essentially the same name, but we call it modified. We can't call it an electron pair shape because an electron pair shape has nothing but pairs of electrons out here on the periphery. Okay? And it's not yet a molecular shape because a molecular shape doesn't have any electron pairs at all. So the next step then is to redraw the same thing. We redrew this to get to this. Now we're going to redraw this to get to the next thing. And in this step, then, we're going to get rid of the lone pair. Now, a word of caution here. Students, a lot of times, just skip over steps. They don't draw that lone pair up there, and they don't get the right, and they end up with the wrong shape at the end, and so they lose points. If you do this process step by step by step, you have a really good chance of always getting the right shape. And if you label everything the way I've taught you to do that, you should have a really good chance of naming it correctly. So if you follow the steps that I've designed for you, you should have a really good chance of being able to do this right every time. And then when you get to college, do the more complex stuff, you can just build on it. Okay? You might not remember all this, but it'll become, you'll remember it as you get into it. Okay? But they probably won't tell you all the things that I'm telling you, but you'll remember how to do this, and it'll help you with the future things you got to do. Okay? And if you need help, you know, you can just email me and say, where do I find this stuff? And I can tell you where to find it. Okay? So here's the shape we have. This is now the molecular shape because now we've got rid of all the lone pairs. Okay, now that's not a tetrahedral anymore. A tetrahedral has 4 arms. Trigonal pyramidal, yeah, good. You didn't pronounce it quite right, but that's good. I understand what you meant, okay? Trigonal, and there's 2 kinds of trigonal shapes, okay? And this is called trigonal pyramidal. And that's the molecular shape. The other kind of trigonal shape is called trigonal planar. Okay? But that one's flat. This one's puckered up kind of in the middle. It's kind of like a little hill in the middle there. All right?
So when you use the bent,
What now?
where does the bent come in?
There's 2 ways to get the bent. One starts with a tetrahedral and one starts with a trigonal planar. Okay? Let's do one that starts with phosphorus, just like we did here, okay? That good? How about we do phosphorus and sulfur and chlorine? Okay, so we still got phosphorus and chlorine, but we're going to use a sulfur here. Okay, phosphorus and sulfur and chlorine. Okay? And we said earlier that phosphorus had 5 valence electrons. And sulfur we haven't talked about yet. And chlorine we said had 1, 2, 3, 4, 5, 6, 7 electrons. Okay? Let's see. Kelvin, how many valence electrons, how many electron dots does sulfur have? Good. Let's see, let's do 1, 2, 3, 4, and then pair up 5 and 6. Okay? Now, when you get to a molecule like this, you might try to share electrons and you're saying to yourself when you get done, wait, this isn't working. And sometimes it doesn't. The first time you try might end up being the wrong way to do it. Leave that drawing on your paper and do it a different way until you find a shape that actually does work, or a sharing arrangement that does work. So this is the electron pair, or these are the electron dot notations, or electron dot formulas. What we want to do now is the sharing arrangement. So I already know, because I've done this enough times to see ahead where we're going, that I have to share twice between the phosphorus and the sulfur. And I have to share once with the chlorine. Okay? And that will give all these atoms 8 electrons. Or at least it had the number of electrons it started with, and when it shares, it has a total of 8. So sulfur had 6, it shares 2, it's got 8. Phosphorus had 5, it's sharing 3, it's got 8. Chlorine had 7, it shares 1 electron, it's got 8. Okay? So we're going to have an octet in the valence level, the highest energy level for all these atoms. Okay? So now we have a sharing arrangement. From the sharing arrangement, we do the Lewis dot formula. So I'll put chlorine over here, and the lone pairs have to stay on here, but the shared electrons get squeezed between the atom symbols. This phosphorus has a pair of electrons here. It's not shared with anything. The 4 shared electrons here, okay, between phosphorus and sulfur, there's 4 electrons shared. They are grouped in between the phosphorus and the sulfur in kind of like 4 corners on a box, or 4 corners on a square. Okay?
What do you know when to put the 4 between?
Well, when I'm sharing 4, I put 4.
And then when you write the sulfur, you'll leave like a side of it blank, right?
Yeah,
Okay.
yeah. That's one way to think about it. Okay? And so I've got 2 lone pairs on the sulfur. And there's a reasonable Lewis dot formula. Okay? In college, they may want you to move some things around a little bit, but that's the way that we can do it in here. Okay? It's a place to start. All right? Then, now we've got to identify how many sets of electrons we have for this. Well, we've got a lone pair up here. There's a lone pair. That's one set. We've got a shared pair. That's a set. This set of 4 is a set all together. All the electrons grouped together between 2 atoms make up a set. So you can have a set of 2, you can have a set of 4, you can have a set of 6. You can have more than that. We don't do that in here. But this is a set. All the electrons between 2 atoms make up a set. Okay? Once you identify how many sets you have, then you can figure out what the shape is for the electron pair shape. We need a shape that has 3 arms on it equally spaced. Okay, so let's see. Coleman, what's the shape that has 3 arms on it equally spaced?
Talking about the tetrahedron?
No, tetrahedral is 4 arms. So that's 4 arms there. I need a 3-arm shape. Well, phosphorus will be in the middle, but I want to know the geometry name of this next shape.
I don't know how to say it.
Well,
TRI
try.
something.
Try. She mispronounced it a while ago. What would you call it?
Trihedral.
Well, trigonal.
Trigonal.
Okay. So you're close. It's called, but this is going to be a trigonal planar shape. I'll draw the shape first and then put the name under it. Okay. So phosphorus is in the middle. You're right about that. Okay. And we've got one set of electrons going up here, one set of electrons going over here, and one set of electrons going over here. So nothing's coming out from the board or going up behind. So this is a planar shape. It's flat on the paper. Two of these arms have 2 electrons on them. 2 of these arms have 2 electrons on them. And one of these arms has got to have that set of 4 right there. All right, so this is trigonal planar. And this is the classification of drawing is an electron pair shape. Now, I didn't write down over here that this is an electron dot formula and a sharing arrangement because I did that in the first set, okay? Since I've already done it for you once, you should now know this is a Lewis dot formula, okay? Well, we've done it several times, a bunch of times. I'm just not labeling it this time for those two, but you might have to do that because we did that in this class. If I teach it to you, you might have it on the test, okay? All right, then I've got this one done. What's the next thing I need to do, Mark Wall?
Can you repeat that?
What's the next step? What do I need to do next?
Make another model of the same thing.
Okay, that's a good way to put it. I would say make another drawing of it, but it's essentially a model, sure. Okay, so we're going to redraw exactly the same thing. All right. Let's see. So Aaron, what do I do with this now?
Change or replace the electrons with the
Okay. We're going to take off some of the electrons and replace them with the element symbols. We only replace the ones that are actually shared. Okay. Don't take off anything or exchange anything that's not shared. So of the 2 pairs here and here, one of those is shared, and it doesn't matter where you put the one that's shared. You can choose to put it on the top or this side over here. But the side with the sulfur has to be the one where the 4 electrons are. Okay? I'm going to put the chlorine over here, and I'm going to put the sulfur over here. I have to put it over here. So we've got sulfur and phosphorus, and this should be sulfur over here and chlorine right there. I got that backwards, didn't I? Because I had to have the chlorine where the two electrons were. And then the lone pair up here has to stay a lone pair right now. Okay. Josiah, what is this thing called? What is this shape called?
Modified trigonal electron pair shape.
You got all the words there, but we're not quite there. You left off one word, okay? It's trigonal planar. And it is a modified electron pair shape. So you had the order of these things kind of turned around a little bit. All right. Okay, Jesus, what's the next thing we got to do?
You gotta get rid of the lone pair.
Okay, so what's the first thing we do to get there?
You draw like another.
Yeah, got to draw it again.
Yeah.
Okay. So I got a chlorine and now I'm going to the phosphorus, and now I'm going to the sulfur, and now I'm going up here with that pair of electrons. And then what we're going to do is we're going to eliminate this lone pair. Now, a lot of times students think, I don't need to do that, and they end up with the wrong shape. So I'm encouraging you in the strongest possible way, please do the steps where I'm teaching it to you, okay? I haven't seen too many students that did it what I showed them to do, they got the wrong shape, okay? But students, they skip things and they miss things, okay? So if you'll do that, you'll probably do a lot better. I can't promise you'll do, get the right thing, but you'll have a much better, higher percentage chance of getting the right thing. All right, Matthew, what's this shape called?
Bent electron pair shape.
Well, bent's right. We've gotten rid of all the electron pairs.
Molecular pair shape.
Molecular shape, right.
Joe, we didn't ask you over there.
All right. Yes.
So, it's okay to put the chlorine on sulfur?
Yeah, sure. You still get a bent shape. It's just up here and over here. Or you could be up here and over here. Okay?
If it's gonna get erased anyway, do we technically have to draw the lone pair? Or
Am I going to look at the little lines and see if you drew it? No.
are you just showing just
But
sure?
I'm telling you that students who don't draw that pair to a much higher percentage of chances that what they do is they will not draw that pair and do a linear shape or something. Okay? And students think, I can do this, I don't need to do it, and then they don't do it right on the test. So I'm trying to help you do it right on the test. Okay? At this point, it would be in your best interest to do everything I teach you to do. Okay? And then after you have done this over and over and over again, you're better equipped to skip those steps when you need to. In fact, you could probably, after you do this enough times, you can look at this and say, oh, I can tell you what that molecular shape is going to be, because I can kind of see ahead of time where it's going, because I've done this enough times. In fact, I chose this formula off the top of my head because I knew that's where we're going to. Okay, because you asked about a bent shape a while ago. All right, because I do it a lot. All right, I've been teaching this stuff for 20 years. So I can sort of do it in my head. All right. So do we need to do more molecular shapes, or is that kind of, you want to see the process and that's it? Yes.
I have a question. So when you do the first step where you share,
Yeah.
does it always equal 8 on each molecule?
Except for hydrogen, almost always yes. There are exceptions. Boron's kind of strange, but I won't give you boron. Boron actually only shares to get 6, depending on what molecule you're making. Okay, so we won't use boron for anything in here. Okay, I'm trying to give you the simple stuff that gives you, a predictable end, and then you can deal with those complex things later on. Okay, yep.
So if we skip the Lewis formula, are you going to take points off?
Yeah. Yep, this is worth 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points, and the name itself, Lewis dot formula, is worth 3 points.
Yeah, that's the Lewis dot.
Yeah.
I'm talking about the Lewis.
Oh, no, I won't count off for leaving the Lewis. If what you're trying to do is find the molecular shape, you don't have to do that. I'm sorry, I misunderstood. I apologize. Okay. Any other questions about this then? All right, then what else do you want me to cover? Yes.
Hybridization.
Okay. Well, while we're right here, let's talk about hybridization, just predicting it from a molecule, okay? I think I gave you these steps already. That if I have one double bond, not 2 double bonds on an atom, but 1 double bond on an atom, that has to be sp2. Okay? So the phosphorus has to be sp2, and the sulfur has to be sp2. Yes.
Could you show us like that we got the answer on the test?
Yeah.
Like hybridization?
Tell me what the hybridization is on these atoms. That's a question.
That's how that would work.
Huh?
That's how that would work. Would you
That
show
might.
us- Would you show us like the dot formula?
If it were this kind of question, sure. It would depend. My question might be, if an atom has one double bond on it, what is its hybridization? sp2. Okay. Now this atom doesn't have a double bond on it. Okay. It only has single bonds and lone pairs. That hybridization has to be sp3.
Say that. Reiterate.
An atom that only has single bonds and lone pairs. No double bonds, no triple bonds. Its hybridization will be sp3. Now that's for the molecules we deal with in here. There are molecules in college that will be a little different sometimes. Okay, but this is kind of like the place to start from. Okay? Got it?
Yeah.
All right, let's look at this molecule then. Based on those, so I've got three rules here. I've got one rule for sp2, and sp3. If I have nothing but single bonds and lone pairs
SP3.
on an atom, that's sp3. If I have only one double bond on an atom, that's
SP2.
sp2. If I have a triple bond on an atom, that's sp. Or, this is kind of rare, but we saw it with carbon dioxide. If I have two double bonds on the same atom, that's also sp. Okay?
What's the question?
What will be the question? If I give you a structure, tell me what the hybridization is.
What would be the hybridization for that one? Yeah, that one.
Is that right there?
Yeah.
Well, what do you think it would be?
SP2.
Actually, it's only lone pairs and single bonds, right?
Oh,
sp3, yeah. How about this chlorine right here?
SP3.
Mm-hmm.
The rest of the ones will also be SP3.
Oh man, you get ahead of me here.
Sorry.
Okay. There we go. Huh? If we were trying to write the orbital notation for these, well, let's take this and look at it here. All right. So let's take let's take this one first. Let's take the phosphorus here. Okay. So phosphorus is on the third row of the periodic table. That means I got to have electrons in 3 primary energy levels. Okay. Helium belongs over here when we're talking about these orbital notation things, the SP, D, and F sublevel regions. So that tells me by looking at the periodic table that I need a 1s electron and another 1s electron. So the first energy level in orbital notation is 1s and 2 electrons. And the 2 electrons are pictured here as arrows to show that they have opposite spins, because electrons have the same charge, and things with the same charge can't be in the same region. They fly apart. So we give them opposite spins to cancel that electromagnetic repulsion. Okay? And then in the second row of the periodic table, called a period, okay, each row is called a period, I've got s electrons and p electrons. So I've got 2 s electrons and 6 p electrons. So the second period, I've got 2 s electrons, and the s sublevel only has 1 orbital, so that's the s right there. P sublevels have 3 orbitals. And in this case, I'm trying to get down here to phosphorus, so all of this has to be full. 1, 2, 3, 4, 5, 6. 1 in each box, 1 in each square, and then you go back and pair up. We're finally now at the third level, the third primary energy level, which corresponds to the third period where phosphorus is located. I have 2 s electrons because I go through sodium and magnesium. When I say 2, I'm counting them 1, 2. It's in the third level, So it's the 3s, 3 primary level, s sublevel, but 2 electrons, 1, 2. And then when I get to p, that's 3p. 3p, I got 3 orbitals. And I put 1 electron in each orbital, and I stop when I've got enough electrons. Well, there's the 5 valence electrons there. I stop. The valence electrons are those in the highest energy level. 3 is the highest energy level.
And then you go back.
Okay? And then we were going to do an sp3 hybridization here. Okay? So we're going to hybridize it to sp3. To hybridize it to sp3, the s right here is like you're implying a superscript 1 on the s. I don't write a superscript, but there's an implied superscript 1. That means we have 1 s orbital. Well, we're only talking about the valence level. So this is the valence orbital we're going to hybridize. And then the p3 means I have 3 p orbitals that I'm hybridizing. So we're hybridizing all of these, 3 of them. That's 1, 2, 3, 4 orbitals. We put 4 orbitals together. And that's called, that hybridized set of orbitals are called sp3s. The valence level is 3. These hybridized orbitals are in the 3rd level, or energy level, 3rd primary energy level. You count all the electrons, 1, 2, 3, 4, 5, and you put them in here like we did with the p orbitals, 1 in each orbital, and then go back and pair up 1, 2, 3, 4, and 5. And that's an sp3 hybridization, or a set of sp3 hybrid orbitals.
It's going to be 3sp3.
Well, 3 just means I'm in the 3rd primary level. Okay? Now, I didn't put in the lower level, so really the whole thing, I'm just hybridizing the valence level. The whole thing, the whole orbital notation would be phosphorus, because the lower level doesn't change. So if I ask you to show me an sp3 hybrid set of orbitals, or the hybridization for the orbital notation of phosphorus, you'd have to show me all this. So the lower levels don't change. That's exactly the same here and here. We put this hybridized set of orbitals on the end of it here because that's what we changed. Does that make sense? Now for sp2, we still start out with the unhybridized orbitals. Okay, so what I did was to redraw this same unhybridized set of orbitals here, okay? And I'm going to show how we get from that to an sp2 now. Okay? So the lower level, below the this 3 is the valence level. These orbitals here in the lower level don't change. If I'm going to hybridize sp2, what that means is we're going to hybridize ns, and the only thing you hybridize are valence orbitals, and that's the 3rd level, so this is the s orbital we're going to hybridize. And we're going to hybridize 2 p orbitals, so 2 of these p orbitals will hybridize, but we're going to leave 1 p orbital unhybridized. So we're not going to hybridize this last p orbital. So we'll have 3 orbitals grouped together, and that's our sp2 hybrids right here. And we got this p orbital over here that's not hybridized. These are going to be our hybridized orbitals. And this is our unhybridized p orbital we didn't change. This is in the 3rd level here. It stays in the 3rd level. The hybridization occurs in the valence level. The valence level for phosphorus is 3. Now I just count all the electrons, 1, 2, 3, 4, 5, and I put them in all 4 of these orbitals in order. 1, 2, 3, 4, and 5. Now before I go forward, I want to go back to this previous hybridization, sp3. Lone pairs and sigma bonds must come from hybrid orbitals, or stem from hybrid orbitals. Lone pairs and sigma bonds must stem from hybrid orbitals. Since I have 4 hybrid orbitals, then this orbital here that has 2 electrons already in it, that's the lone pair. These 3 hybrid orbitals then that have 1 electron in there, those become sigma bonds. If I look at the molecule, there's the lone pair. There's our 3 sigma bonds. Yes?
Must stem from what?
Lone pairs and sigma bonds must stem from hybrid orbitals. Now I wanted to reiterate that, or go back to that, because here I have 3 hybrid orbitals and 1 unhybridized orbital. So you can get a lone pair here, you can get 2 sigma bonds, but this cannot be a sigma bond. This has to be a pi bond. Okay? Now pi bond and a sigma bond together make up a double bond, and there's the double bond right there. That makes sense?
Can you go back up to the phosphorus?
You mean, oh, right here?
Yeah.
Okay. So this will be a lone pair. This will be a sigma bond because I got 1 electron in it and it's a hybrid orbital. This will be a sigma bond because it's a single electron in a hybrid orbital. But this becomes a pi bond because p orbitals can become pi bonds, but they cannot become sigma bonds or lone pairs.
And how many? Is it just like empty?
Say what?
Is it just like empty? But not empty, but
Empty. It's got 1 electron in it.
okay.
Let's see. Suppose I have silicon and phosphorus and chlorine. I could go through the whole sharing range, but I'm going to skip right to the Lewis dot formula. In the Lewis dot formula, then we'll have chlorine and silicon and phosphorus. Oop, I should have made a little more space in there, but that's all right. I want to have 3 pairs of electrons in here. That's a triple bond. Can y'all see that, or need to redraw it? Need to redraw it? You can't see it? You can?
I can.
I'll do that. Chlorine first, then chlorine and silicone and phosphorus. And I'll put 3 sets of electrons in here. 2 electrons here.
And that's still one set?
Yes, that's 1 set.
How come the silicon is in the middle?
What now?
How come the silicon is in the middle?
Because in the case of this molecule, everything's bonded to the silicone.
Okay.
If you put it won't work out. If we did the electron dot notation in the sharing arrangement, it wouldn't work out to put phosphorus in the middle.
Mm-hmm.
I'm just kind of skipping over all that to show you this, okay? So here I've got a triple bond. All right, now we were talking about if I had a double bond here, it's got to be an sp2 hybridization. If I've got a triple bond on an atom, that has to be an sp hybridization. So both the phosphorus and silicone have a triple bond attached to it. The chlorine only has single bonds and lone pairs. So what kind of hybridization is the chlorine?
SP3.
sp3. Good job. Okay? Does that make sense? What else you guys want me to cover?
We've done hybridization. We've done the molecular shapes and all that.
We've done some molecular shapes. We've done some hybridization, yes.
What else is on the plate?
Well, let's see. We kind of started the unit with hybridization, so that might be on the test with the orbital rotation. We did balloon models, so that might be on the test. We did molecular shapes, that might be on the test. Might. Didn't we draw it in here?
Yeah.
Yeah?
Oh, dang, that's tough.
That's the shape of bonds.
Can we let go of it?
Sure. So this is a single bond. What kind of bond is, we're talking about the shapes now, what kind of bond is a single bond? Sigma. Okay? So between the phosphorus and the chlorine, if I'm sharing just 2 electrons, I've got to have a sigma bond. So for this bond here, that's a sigma bond. The symbol for sigma is,
The old squiggly line on the end.
yeah, I got 2 electrons in there. Okay. What's the hybridization on the phosphorus? sp3. And the hybridization on the chlorine? Well, chlorine's also sp3 here, right? Okay. All right, that's one of the sigma bonds there. All right. Then I've got a sigma bond that's kind of coming out toward me. There's 3 sigma bonds. One's on the paper, one's coming in front, one's behind. So I've got one that's coming out toward us. Trying to show an orientation that's kind of coming out toward us here. That's a sigma bond. 2 electrons. sp3. And the chlorine's out here. And it's sp3. And then I got to have a sigma bond that's going back behind things. So that's this bond right here that I'm picturing like this when I'm talking about the shape of bonds. Okay. And I'm gonna have to kind of put it above it here because I don't have room to put it in it. I'll put SB3 here and SB3 here. And then I've got a lone pair of electrons here, here. How do we draw the shape of a lone pair of electrons? A round balloon. Yeah, not a long balloon. Long balloons become either this or pi bonds, okay? But the round balloons are where what the lone pairs are supposed to look like. So the lone pair might look like that.
How long was this unit?
What?
How long was this unit? Like, was this like a whole week?
We spent close to 2 weeks on this.
That's what it was like 3.
I should say one lone pair, not pairs, not plural. This molecule here has a double bond. Actually, I should put that kind of down a little bit, not straight on a straight line. Let's put the phosphorus here and the chlorine here and the sulfur here. Okay. All right, I want to look at the double bond first. Okay, the double bond has to have a sigma bond and a pi bond. That's what makes up a double bond. So I've got hybridized orbitals here for a sigma bond, and I've got a pi bond, a p orbital unhybridized for a pi bond. The hybridized orbitals are single balloon shaped. So the phosphorus to the sulfur, they have to have some hybridized orbitals kind of pointing toward each other. When they join together, it becomes that long balloon shape or that hot dog wiener shape. Okay? So any bond directly on a line between the nuclei of two atoms is called a sigma bond. There are 2 electrons in there.
Can you say that one more time?
Which one? About the sigma bond?
Yeah.
Any bond directly on a line between the center of 2 atoms.
Any bond directly on
Line between the center of 2 atoms is a sigma bond. Now in textbooks and in college, they'll call that, instead of calling it a line, they'll call it an axis. Okay? And there's a reason for that, but at this point I don't want to try to stop and explain the difference between an axis and just a line. Okay? All right then, we've got this p orbital that's not hybridized. And for a double bond, I got to have a p orbital not hybridized on the s and the p. Okay? What's the shape of a p orbital? Ginger, what's the shape of a p orbital? We made balloon models of p orbitals in Unit 2.
Wait, I'm sorry. Say that again. What's the question?
What's the shape of a p orbital? Ginger's trying to remember.
Is it the longer one?
What?
The longer one?
No, a p orbital is not a long balloon. A p orbital, that was 6 balloons?
Oh,
3 colors?
Yeah.
It's back there on my table.
Oh, don't tell her
I don't know
that.
what it's called.
It's a double balloon shape. That's one way to describe it, okay? So the p orbital will be like this, okay? I'm trying to help her to draw it out of her brain, okay? It's in there somewhere. Just trying to help her to recall that. Okay, that's the whole point of me calling on people to answer questions, to get you to, draw it out, okay, and try to connect with the knowledge. That's the whole point of a test review, isn't it? All right, so we got two p orbitals, and these p orbitals are parallel to each other. The resulting pi bond is going to be parallel at 90 degrees to those. Okay? So let's see here. The pi bond then is here and here. It's one pi bond, but there are two antinodes to make up the pi bond. So this is a pi bond, and it came from a p orbital. Which axis do we want to put this p orbital on? X? And it doesn't matter, you can choose one, okay, because we don't, all we got to do is make sure that X doesn't conflict or be the same as Y. You can't have two pi bonds on X.
So as
Yeah.
long as they correspond, they're okay.
Huh?
As long as they correspond, they're okay.
Yeah, that's one way to think about it. So this would be pi X, and we got two electrons in it. Okay, so there's one bond, there's a sigma bond in the double bond, has two electrons, and one bond that's the pi bond that has two electrons in it. Okay, that's the double bond right there. Then the sulfur has two lone pairs on it. So I'm going to put a lone pair coming out in front here like this. And I'm going to put a lone pair back behind that. So this is a lone pair. The lone pair has two electrons in it. The s orbital is sp2, so this is going to be sp2. This is going to be sp2. So all the lone pairs and sigma bonds stemming out of the that atom have to be of the same hybridization. Okay, and so this lone pair in front also is sp2. And the phosphorus has a sigma bond, a single bond is a sigma bond, going to the chlorine. So let's see, let's make this like this. So this is going to be a sigma bond. The phosphorus had a hybridization of sp2. That makes this sp2. But the hybridization of the carbon is, what is it? I'm sorry, on the chlorine. What's the hybridization of the chlorine?
Oh, wait, is that a 3?
That is a 3. sp3. Okay, the one thing we haven't drawn yet is the lone pair. Okay, so there is a lone pair on this thing. All that makes sense? So there you have some models of the shape of the bonds themselves, or drawings of the shape of the bonds themselves. And now, I don't expect you guys to have, perfect angles and things like, just like, because I've been doing this a while. I understand more about where how to arrange lone pairs and double bonds and things like that. But it has to be, fairly reasonable. Okay, got it. All right. What else do you want me to cover?
Y'all wanna start Unit 4?
No.
No, we gotta eat.
I will start Unit 4 now if you don't have questions.
I have a question. Can I ask questions about the practice test?
Yeah.
Alright, so I didn't understand how you worded numbers 55 through 50,
We'll just read 55 through what?
58.
Okay, so read 55.
Determine the hybridization of the sulfur and sulfur difluoride. Show all your work.
Okay, so what we need to do first of all is to find out what that looks like. We can use electron dots. Okay, so sulfur has 6 electron dots, and it was difluoride. Okay, and so fluorines have 7 electron dots, and there was 2 of them. And so I need to get to how many electrons here on each of these tyranny? How many electrons in the valence level do these, or dots do these atoms want to have?
8.
8. So I share here, one here, and one here. And that gives all the fluorines the 8 they want, and it gives the sulfur the 8 it wants. Okay? And then I can do a Lewis dot formula. And now we just apply those rules we talked about earlier, right? So, what is the hybridization on the sulfur?
SP3.
There you go. So sometimes you just have to kind of, do the work to get there to figure it out. You can't just, there's no memorization for this. If you're doing it as long as I have, I can probably think about it in my head, but you have to actually lay it out to figure it out. Okay, what does 56 say?
Oh, I understand it now.
Okay,
It's basically
all
the
right.
same. But 57 says an atom is triple bonded to another atom and has a lone pair of electrons. What is this hybridization?
SP.
Because I gave you the rule a while ago. An atom that has, I gave it to you earlier actually. I gave it to you last week? No, maybe earlier this week. I forget what day it was. But I said that anything with a triple bond on it has to have a sp hybridization in this class.
Or
And-
what else can have a SP, you said?
If you have 2 double bonds on the same atom, that atom can have an sp hybridization. But if any atom with a triple bond has an sp hybridization. And we did one molecule. That's the one that's most common. That's really kind of rare where you have 2 double bonds on the same atom. For reasons I won't get into in here. Okay. What now?
What time does lunch start?
What time is
Does lunch start?
1:05?
Are we third
Why
lunch?
is it starting so late? I thought you had.
Because they had to divide it up into 2 different lunch periods. And they have to work it out to get them delivered, and all that kind of stuff. So that's why.
What if you forgot to order?
What?
What if you didn't order?
What if you didn't order? Well, I guess you're kind of stuck, but I suppose, we can send you down there later.
Or you can do the lunch order online. You can still do it online.
Can you still do it online?
Even if it's late, you can still do it.
I thought you could only do it through the second period.
No, it's closed.
Is it closed? Okay.
I can go down
What they've been saying is if you order and get into your order, I'll send you down there. I suppose when they call on that, I can send you down there. Okay? Well, in other words, if you haven't ordered at all, I haven't been given any direction on whether to send you down there or not. You can't go down there right now. You got to wait until they call for people who didn't receive their order. That's the deal. As I understand it, that's the deal. Okay? So a lot of the things that I've been kind of giving you guys ways to do things here to make things easy that I'm told now that I really can't do for you guys. So I'm trying to stick with the rules. Okay? All right, you got a question? Go
When
ahead.
it says describe the shape of a bond, how do you want us, how do you expect us to describe something? Like a sigma bond?
Okay. How would you describe this? That's a sigma bond.
I don't know I don't know.
Really?
I don't know the descriptive words to use.
A long balloon, a hot dog wiener, a cigar.
So you want like a literal shape name?
It depends on the question. If the question is, what's the shape of a sigma bond? Yeah, I'd call it one of those things. Huh? Wait a minute. I got a bunch of people talking at one time. You think I can hear all that? Help me out. If you want to contribute, raise your hand. I'll call on you. You got another name for it?
Oval?
An oval? It's not really an oval though. It's more elongated than an oval. And an oval still is planar. This is three-dimensional.
So
Yep.
how do you describe
Please be quiet. Individual conversations, can't do that because we're reviewing for the test, okay? Go ahead.
So how would you describe a pie bond? Like, what would you personally describe it as?
If I was calling this a hot dog wiener, I'd say this is the bun.
Banana.
Bananas. 2 bananas.
Which one? Those right there?
The pie bond.
She's talking about the pie bonds here.
Oh yeah, they look like vampire things that you put in like for Halloween. That's what they giving me.
Yeah.
As long as it's a reasonable description, for that question, I'd accept it. Why is my computer doing this strange thing with this? Don't even use it in Google Meet today. Anyway, all right. Anything else?
Y'all want to start using for? I mean, it's kind of.
I have one more question for the practice test.
What's your question?
All right, so number 63, it says, how can atoms get 2 electrons?
All right, hold on. You got to hear the question. If you're talking, you can't hear the question. Go ahead.
It says, how can atoms get 2 electrons in the same orbital when like charges repel?
If one is positive, the other one is negative.
Well, it's not positive and negative because electrons are always negative. Hang on a minute. Let me restart a program here that maybe I can get the camera going and keep it going. I don't know why this thing is doing this crazy stuff. Until I started using Google Meet, I didn't have this problem. All right. This is an illustration of exactly that answer right there. How did I get 2 electrons in the same orbital? Crazy. How did I get 2 electrons in the same orbital? What are those arrows picturing?
Electrons.
They're picturing electrons, but what about the electrons are the up and down arrows picturing?
One's negative, which means they have a valence charge.
Well, you're not really far off. If we were doing, what are they called? Quantum numbers, we might symbolize it as positive, negative, but it doesn't really mean a positive charge and a negative charge. All electrons have a negative charge. Somebody said it a while ago.
The way that they're spinning and
The way they're spinning, it's an opposite spin. The opposite spin of the electrons is the way we describe how 2 electrons can cancel the electromagnetic repulsion. Particles with the same charge repel each other.
So
Okay?
how do atoms share more than 2 electrons between them?
How do 2 atoms what now?
If electrons have a negative charge and if 2 electrons can be in the same orbital or bond by having opposite spins, how do atoms manage to share more than 2 electrons between them in a double bond or a triple bond?
Okay, they're not in the same space.
Not the same space.
No, they're in different places. That's why they have to have a pi bond, to make that happen. According to Vesiper theory. Y'all do remember what Vesiper stands for? Well, tell Matthew over here. He doesn't remember.
I didn't know from the jump. Go ahead and tell me.
Wait, how about just one person? Because too many people, even I can't hear you. Ginger, why don't you tell him what it means?
It's valence shell electron pair repulsion.
Yeah, I pronounce it valence, but the young lady that's doing the clinical teaching here, she calls it valence. Okay, my professors have always called it valence. I don't know which one's right.
Oh, on my practice test, that question wasn't on there.
Yeah, if you look at the instructions in Google Classroom, I added that question in there. Okay, because I realized once I publish it the way that I publish it, where I give you a copy, I can't change it then. So I added that as an extra question in the instructions at the top. That's why you got to read the instructions. Yep.
So, the things we were doing yesterday, the monoatomic ion
Yeah.
and that stuff, are we gonna have to memorize the words?
Yeah. Monoatomic, polyatomic, cation and anion. Yeah. That's just 4 words, right? Yes, sir.
Cation is positive and anion is negative, right?
Right. Yep. More questions? Well, I'm not going to stop teaching until lunch arrives. So if you don't have questions, I'm going to start on Unit 4
Why would you start Unit 4 with only 4 links here?
because that's what I'm going to do.
Then what if we get confused when it's time for this test? Because we're
That's what I'm going to do. Do you have any questions?
When a version of the
Yeah, I got
cell-
one last question. When then it was hybridized orbit?
What?
What is the pi? When does the pi come in? Like, how do we differentiate a pi? Well, I know how to differentiate from a long pair from a pi, but what do you say?
Well, that's okay. What were you saying?
I said for like a pure orbital.
Well, that's where they stem from that. Pi orbitals always stem from unhybridized p orbitals. Okay? But if that's your question, that would be the answer. But my answer, the way he asked it, would be that where do they come in? They come in anytime you have a double bond or a triple bond. If you only have a single bond, that has to be a sigma bond. Okay? There always has to be a sigma bond with any kind of bond. So if you have a single bond, that's a sigma bond. If you have a double bond, you have a sigma bond, then a pi bond. If you have a triple bond, you have a sigma bond and 2 pi bonds. Does that make sense?
Mm-hmm.
So if you're asking when does it come in terms of what kind of bonds result in that,
I'm talking about the drawing part.
okay, then I guess you're talking about it comes out of a p orbital. Is that what you're asking about?
Not really. You were on the right track.
Okay. I thought that I've answered it, I guess, haven't I?
Yeah.
Yes.
Can you go over crystal shapes or whatever we went over like yesterday?
The shapes or how they...
How they form.
Okay, well, anytime you have a positive and negative charge, and that would be ions. Okay. In fact, there are other kinds of crystals. We're only right now dealing with the ionic crystals. And they're, so in terms of the way Matthew was asking that question a minute ago, those come in when you have an ionic compound. And there are some ionic compounds that don't form crystals, but most of them do. Okay? So you always have to have alternating positive and negative charges. And sometimes you got a 2 positive and a 1 negative particle. Okay? Sometimes you got a 3 positive and 2 negative particle. And they arrange themselves in a little bit different way, but they still make a crystal. We only dealt with a really simple crystal. Okay? There's a name for that. It's basically the simple one we talked about was where you had positive alternating with negative, positive alternating with negative. That makes sense? And then they keep going, growing and growing and growing. Now, so when I say positive and negative here, that doesn't necessarily mean a one positive and a one negative. It can be any kind of positive and any kind of negative.
Does it have to match like 2 negative, 2 positive?
No,
Just
you can have different charges, but the ratio will always be neutral. So that if one particle is 2 positive, then I have to have 2 1 negative particles for every single one of those 2 positive particles. Okay? So we spent some time going over and drawing how those things arrange themselves. You need to be able to do that. Okay? I wish we had time to do that or could do that lab, but we can't do that lab. I've got models that'll actually make those. Yes?
So if we spell something wrong on the test, are you going to take points off?
That depends on how far off it is. Well, I mean, if you spell covalent, S-T-I-C-K, I'm not counting that. You know? But if it's reasonably close, you know, I guess I can handle that. Okay?
Yeah, we abbreviate.
No. Are there times you can't abbreviate? I'll accept it, maybe, but I wouldn't take the chance. Because I might not know what your abbreviation means. Okay?
Okay.
I'm trying to make sure you get all the points. All right? You know, sometimes I've had some, I don't know, people they have strange abbreviations and I can't figure out what they mean by it. If I can't figure it out, it doesn't exist. So don't leave me scratching my head. What does this mean? Okay? Be clear for me. All right. Well, our next unit is called nomenclature. The lunch isn't here though, is it?
Wait.
I can't deliver the lunches. I'm still teaching.
Okay, then what causes a polyatomic ion to have a positive or a negative charge? I really didn't answer that.
Well, it's the same as an atom that has a positive negative charge. If you have more protons than electrons, it's positive. You have more electrons than protons, that's negative.
Okay, so it's just that simple?
Huh?
Is that simple?
It's that simple. Listen, always look for the simple answer first.
There's
Most
no
of,
simple answer in here.
huh?
There's always some tricky stuff.
That was simple.
What was the question? It was, what causes a polyatomic ion to have a positive charge or a negative charge?
And what was your answer?
If you have more protons, you got a positive charge. If you have more electrons, let me finish, please. If you have more electrons than protons, then you got a negative charge. Electrons are negative, protons are positive. It's the same as an atom. An atom has an equal number of protons and electrons. If you take away an electron, now it's got more protons than electrons. It's a positive charge. It becomes a positive ion, a cation. If you add an electron to it, then it's got more electrons than protons. Electrons are negative, it becomes an anion.
Isn't this unit 4?
Oh, so you're right. This is unit 4 is nomenclature. Nomenclature. Here you go. Nomenclature is
Wait, how do you
a naming system.
What is that called?
Nomenclature.
What?
Nomenclature, a naming system. What now? Well, I can't make it come here. I don't know on this program how to zoom in right this minute. I haven't used it in a while. There's, well, it can, but then I start getting focusing problems, and then I have to pull it back out again. So,
Can you spell that out loud for me? I can't see it.
You just spell it aloud or something?
N-O-M-E-N
You what? N-O-M.
E-N
Mm-hmm.
C-L-A
Mm-hmm.
That's a E.
T-U-R-E.
A naming system?
Yeah, it's a naming system. What species are you?
Homo sapien.
There you go. That's part of a nomenclature system. Okay?
It's a
But that's a biological naming system. We have a chemistry naming system here. Okay? All right. And this nomenclature system is for naming compounds. We've already talked about elements. Okay? And you have the periodic table with the names on there. In fact, somebody pointed out in first period, and I'd never really noticed this. I guess I never paid attention to it. If you look at the noble gases over here, except for helium, they all end with ON. I didn't realize that was part of the nomenclature for elements.
So they did it on purpose?
Huh?
They did it on purpose?
Yeah. And the halogens all end in INE.
Yeah.
I never noticed that before.
Oh, the bottom layer in IUN.
Yeah. Well, look at all these metals over here. Now, what you don't know that I know is the metals that have been known about for centuries, they have other names. But anything that's been around and like only been discovered in the past 100 years or something, they have an IUM ending. Well, metals form positive ions, and so those polyatomic ions we did yesterday that are positive, hydronium and ammonium, they have an IUM ending because they have a positive charge on them. So it really has to do more with the charge that they get on it as opposed to the metal itself. But that's what happens. That's where it comes from. Okay? So a nomenclature system is a system of naming. And so you can tell a lot about an element, or in this case compounds, by the name. And you can take the formula for a compound and figure out a name. So that everybody's talking the same thing. Okay? So there are 4 classifications, 4 categories for nomenclature. We have to have this covalent stuff we've been talking about. But the nomenclature we've been dealing with for the most part is covalent non-organic or non-organic covalent. There is also an organic covalent system. If you just say organic, that means covalent. Primarily, there's some ionic parts to organic sometimes, but we're not going to get into that. We're going to stick with the really, really simple stuff in organic. Okay? Organic is a whole separate thing. I mean, in college, there's a whole 2 classes worth if you're doing some of the sciences of organic chemistry. And so the young lady that's doing that clinical teaching in here, she's taking organic chemistry right now, and that's a class that wow, that really kicks you, going through that stuff.
Does she want to be a teacher?
Huh?
What does she
It depends on what you want to do. If you're going to be a chemistry teacher or a biology teacher, yeah, sure.
So what does mine say?
What you gonna have?
Okay, so these are the last 2 categories of nomenclature. Please put that in your notes.